Welcome back, ladies and gentlemen. We are in topic 2, still in packet 1, running circles around geometry. This video is for activity 1.1, as you can see here, circle, parts, and bisectors. For this section, you are going to want a compass and a straight edge. If you don't have both of those things, you can still follow along, but it would be great practice for you to go ahead and have those things if you have access to them. So question 1 says, use a compass to construct a circle in the space provided. Label the center point O. So there's a couple ways you can do this. You could draw the circle first and then label the center point. I'm going to go ahead and do the center point first, and then I'm going to do my circle around it. So when you're drawing a circle, remember you just want the compass, the center of your compass, to be, almost ran out of room here, hang on, a little bit of difficulties, there we go. Okay, you just want the center, or you want the point of your compass to be in the center of your circle, and then you just trace around it. My desk wasn't quite as big as I anticipated, so I almost ran out of room there, but we are good to go. So it says use a compass to construct a circle in the space provided. Label the center point O. Boom. Question 1. Good to go. All right, we've done that. Question 2 now. Use the definitions to complete the construction and answer each question. Okay, the definitions are on the right side of your packet. If you took notes in class or if you watched the vocab video, they are also there. The ones that aren't going to be in that video are going to be these very first two, a radius and a diameter. Those ones you've hopefully seen in previous classes, but if you haven't, they are here for you. A radius is a line segment from the center of a circle to the point of to a point on the circle, so center of the circle to a point on the circle. A diameter of the circle is a line segment passing through the center of the circle with endpoints on the circle. So the diameter, if you remember what a chord is a line segment with endpoints on the circle. A diameter is also a chord. The thing that makes the diameter special is that it passes through the center of the circle as well. So here we go. A says construct a diameter of the circle. Label the endpoints D and M. Point O is the midpoint of the diameter. So with a straight edge, we can do this any way we want. I apologize for the shadow here. My light source is kind of just how it is, so I apologize. But to create a diameter, I'm just going to draw a line that goes through that center point. Okay, and then here are my endpoints. And we said that we would label these D and M, so I'm going to go ahead D and M. There you go. So now we have our diameter. So construct a diameter of the circle, label the endpoints D and M. So we've done 2A. 2B says how many central angles and arcs are produced by drawing a diameter and what are their measures? Explain how you know. So at the end of the getting started activity, we talked about what angle makes a perfect circle, and if you remember from that, it says 360 degrees. We said that an angle that starts here, goes all the way around and ends there as well, is a perfect circle, 360 degrees. So if I'm looking at a diameter that cuts this circle in half, okay, first of all, how many central angles and arcs are produced? So a central angle, remember, has its vertex in the center of the circle, and then its sides go out to touch the sides of the circle. They're also, another way to say that is that the vertex is at the center, and then talking about radiuses, we have two sides that are radiuses. So if I start from the center, here's one side that's a radius, here's another side that's a radius, okay? So here is one angle measure, so there would be 1, and then 2, so we do make 2 central angles. So to answer this, how many central angles and arcs do we have? 2, I'm going to put CAs for central angles. And then how many arcs? Well, if you remember, an arc is the distance along the circle, so along the curve of the circle from one point on the circle to another point. So we've only made 2 points, so I can go from D to M clockwise. That's 1 arc, and then I can go from M to D clockwise as well. That is 2. Okay, so there are going to be 2 central angles, 2 arcs. What are their measures? We talked about the perfect circle is 360 degrees, so half of that, okay, so half of 360 would be 180. That would be the angle for both of our central angles, and it would also happen to be the angle or the arc measure for both of our arcs. Okay, so part B, good to go. Here we go. Number C, what name is given to each half of the circle created by the diameter? So this is a vocab word that hopefully you've seen before. It is not on the side of our thing, so I lied a little bit, but not on purpose. Okay, so what name is given to each half of the circle created by the diameter? Basically, another way to word this question is, what is the name we use to describe half of a circle, or a circle that is cut in half? Okay, for that, we're going to go ahead and call that a semicircle. Okay, so anything that is labeled as a semicircle specifically is exactly half of one circle. So a quarter of a circle is not a semicircle. an eighth of a circle, not a semicircle. 1/8, or excuse me, half of a circle is a semicircle. Again, that is, maybe not the best drawing ever, but 1/2 of a circle is a semicircle. Okay, so part 2C, boom, flying through this. Number 3 says construct a perpendicular bisector of the circle's diameter. Label the points of intersection of the perpendicular bisect and the circle as points B or P and B. Okay, so I'm going to go back up here to my original drawing. I'm going to construct perpendicular bisectors. Okay, this is going to be where you're going to want a compass as well. Okay, so remember when we're doing perpendicular bisectors, the line segment that we want to do the perpendicular bisector for, we're going to go to both endpoints. Well, one endpoint at a time. We will end up doing both. I'm going to put the point of my compass on one of the endpoints. And here, let me do this. Sorry, here we go. We are doing this live. Okay, so then I'm going to draw an arc. Okay, and the key about this arc that you want to draw, you want it to be bigger than halfway. So we know that perpendicular bisector is going to cut our line directly in half. We already know that point O here is the center of this line. So I want my arc to be bigger than from M to O. So you can see it is in fact bigger than M to O, so I'm good to go. Okay, and then without changing the size of your arc, you're going to put the point on the other end point, or you're going to put the point of your compass on the other end point that you haven't done yet. And so without changing the size of your arc, you're going to trace an arc as well. Okay, so you can see I have kind of this fish looking thing. Then we're going to go ahead and want to use a straight edge. Again, I apologize for the shadow if it is bad. Looks like it's not too bad at this angle. Okay, and then we are going to, because we have 2 points of intersection, so I want to draw a line that goes through both those points of intersection. Okay, and that will be my perpendicular bisector. So there you have it. Here's our perpendicular bisector. And we said that we were going to label these P and B. So there you go. So now, part 3, all part 3 asked us to do, sorry, throwing my compass on the ground. All question 3 asked us to do was to, here, let me slide it up so we can see it, was to construct a perpendicular bisector of the circle's diameter, which we did. Okay, so we can go ahead and go check on question 3. We will have to keep drawing on this, so you're going to want to keep it out. For now, I need to flip this page over though. Now we're on to number 4. Use the definitions to identify the circle parts and answer each question. So again, our definitions are over here if you need them, if you haven't already written them down. So part A says identify all of the drawn radii, I'm going to circle this word because it's important and I'm going to talk about it in a second, of the circle created by the diameter and its perpendicular bisector. So radii, okay, another way to say radii, and this is not the correct way to say it, so if you're ever in a super high-level math class, okay, radiuses. So if I have one radius, if you remember the radius right here, the radius is a line segment from the center of a circle to a point on the circle, okay, radius. So radii, or radiuses, is if I have multiple. So if I were to draw another straight line like this, okay, instead of having one radius like we did in the original drawing, now I have multiple radii, okay? And I will say radiuses for you just so that you guys don't get confused, but just know that radii, this word, okay, radii means radiuses or more than one radius. Okay, so identify all of the drawn radii of the circle created by the diameter and its perpendicular bisector. So we are still looking at our circle that we've drawn here. Mine's a little off kilter. I can shift it this way to make it straight up and down if you want. It doesn't really matter how you have it, just as long as you have your original diameter and its perpendicular bisector. So I'm looking for how many radii I have. So we said that a radius is a line segment from the center of a circle to a point on the circle. So how many lines do I have from the center of the circle to a point on the circle? Well, if I go OM, that's 1. And so all of these radiuses, or all these radii, okay, should start with point O because, or they should all contain point O, because in order for a radius to be a radius, we need one of the points to be a center point. So OM is a radius, OP is a radius, OD also a radius, and OB is a radius. So we've created 4 radii so far, okay? And so just a real quick reminder, OM, this line segment OM, could also be labeled as line segment MO, okay? And what I was saying about the center is that because the radius includes the center point, all of these line segments will need point O here. So we've created 4 radii, and it says identify all of the drawn ones. So I'm just going to go ahead and say we said OM, OB, OP, OD, and those are all line segments, so I'm going to put my little straight line over those. So those are all 4 of my radii, and then this would just be 1, 2, 3, 4. Okay, so there are 4 radii, and so that's why we have 4 line segments here that we've identified. So part A, good to go. So now for part B, what central angles and arcs are produced by the diameter and its perpendicular bisector, and what are their measures? Explain how you know. So this question, part B, number 4 part B, is similar to number 2 part B, where it asks us how many central angles and arcs are produced, and then what are their measures. So now we've added a few new lines. Sorry, coming back to our circle that we've made. We've added, originally we just had this line, and we said that we had 2 central angles, 1 and 2, and then we had 2 arcs, 1 and 2, and that their measures were 180 degrees. Okay, now we know that we've made a perpendicular bisector, so I know that line PB, line segment PB from top to bottom here, is perpendicular to line DM because we made it perpendicular, right? And so that means that this opposite angle is also perpendicular. That means that all of these angles, okay, are 90 degrees. So when we talk about central angles, remember a central angle is an angle whose vertex is in the center of the circle. So if this is the point of my central angle, and then the central angle sides are radiuses, or radii, right? So there's 1, this top right region, 2, top left region, 3, bottom left region, and 4, bottom right region. Okay, so what central angles and arcs are produced by the diameter and its perpendicular bisector, and what are their measures? So it's asking specifically for the names of these angles. So I just said we made 4, and we said that they all had 90-degree angle measures, so I can go ahead and do that. But now I want to get the name of these angles. Okay, again, because these are all central angles, they will all include O as their vertex. So MOP, angle mop, okay, POD, pod, DOB, dob, and then BOM, bomb. Welcome, ladies and gentlemen. I don't know if you have known frustration until your iPad tells you that you are full on storage. You go into settings and it says you have 11, that is a 1 out of 16 gigabytes used, and somehow you are full on storage. Anyway, so I am back with the second part of this video. A little bit frustrated from that, but here we are. I was just talking about at the end of the last video the 4 angles, central angles that are created here on part B. We labeled them all MOP, POD, DOB, BOM. Looking back at our circle here, we can see all those. Those are our central angles. And then for their arc names, we can either flip it over and look at all those, or another way that we can look at it, okay? So O is at the center of all of these angle names because it is the center point. So all of the other points, M, P, PD, DB, and BM, are going to be points that are on the circle. So arcs that were created by these are going to be MP, PD, DB, and BM. So the reason I know that is because these are endpoints, or these are points that are on the circle. So an arc is created from B to M, so B to M here, D to B, D to B, PD, PD, right? And so on and so forth. And then if you wanted to double check those, you could flip this over and look at these. We do in fact have MP, PD, DB, and BM. All right. So those are the arcs, and then what are their measures? So we said that all these angle measures were 90 degrees. Similarly with all of our arcs, they're also going to measure 90 degrees. And so now we are done with part 4B. Now we are on to 5. It says draw a line through 2 of your labeled points on the circle to form a secant and a chord that is not a diameter. Okay, so here we go. We're drawing a line through 2 of our labeled points that are on the circle. We're going to want to use a straight edge for this. You can use any of the 2 points that are on the circle. D, so we could use PD, DB, BM, M, P. The reason we can't use M and D is because it said we do not want to create a diameter. This that we've already created as a diameter, same with PB. So we want to do something like this. So I'm going to go ahead and do BM for this example. This is different than the one that I did in class. But it is another way that you can do it here. Okay, so I'm creating a secant line that goes through these 2 points. It is also a chord. Okay, so part A, 5 says draw a line through the 2 labeled points that is not a diameter. Boom, we check with that part. A now says use a protractor to measure the angles of the triangle and a ruler to measure the side length. So Okay, we've created this triangle, and then give me 1 second while I dig out my protractor from my bag. Here we go. This is a gigantic protractor. It does work though, okay? So what you have to do, the way that mine works, and it's hard to see because of the shadow, you have to put this point right here, right on the dot, and then you can just go ahead and slide that protractor over until it looks like you are right about on it. Sweet, and so that's kind of hard to see. I apologize for the shadowing, it's just where my light source is. This is in fact, so this angle right here, according to my protractor, is indeed 45 degrees. Okay, we already know that this one is 90. And then because triangles, the sum of their interior angles, the sum of the angles that are on the inside of a triangle add up to 180. I already have 135 if I add 90 and 45 together. So 180 minus 135 is going to be 45 for here as well. Okay, so that is the angle measures here. And now using the inches, okay, using some inches here. Okay, this will be a little bit better. So here we go. This is 6/10 of an inch. Okay, so I'm just going to go over here. OB is 6/10. Okay, or if you wanted to go 3/5 of an inch. Okay, I'm now going to measure, and this one's going to be the hard one because of the shadowing. You're going to kind of have to take my word on this one. This one is also 6/10, and this is OM. And I'll just go ahead and skip the 6/10 and say that as 3/5. And then the length of our final side here. Okay, I'm gonna go, here we go. So from 6, looks like it's about 9/10. If you can see that, my finger was covering it up. So from 6 right there to the dot is actually right under that 9/10. So we would say that this for MB is in fact 9/10 of an inch. Okay, so now we've done that. I should have put this, I should have put these measurements under here, but we did label them, so we are good to go. Now we need to classify the triangle that we have created. Okay, one thing that we know about triangles and their side lengths is that if we have a triangle with 2 side lengths that are the same, it is isosceles. We do have 2 side lengths that match here, and a third one that does not match. That would make this an isosceles triangle. So classify the triangle you've created. We would say isosceles. Okay, sweet. So now we're moving on to, so that was question 5. Now we're going to move on to question 6 here. Give me 1 second while I straighten up my paper. Here we go. Question 6. Compare your circle diagrams with your classmates' diagrams. Did everyone create the same triangle, the same type of triangle? So I would go ahead, so again, I'm going to kind of have to simulate this because I don't have classmates here with me with different diagrams. But did everyone create the same triangle? The answer is going to be no on that one. So you can see that on my circle, I created, or I connected, there we go. I connected lines or points BM together to create this triangle, BOM. If you were to connect lines PM, P and M, then you would have a circle or a triangle POM. Likewise, if you were to connect lines or points P and D, then you would have a triangle POD, right? So not everyone created the same triangle. So did everyone create the same triangle? The answer to that would be no. Did everyone create the same type of triangle? And the answer to that, if you look, okay, if you look at how I created this, we said that this was an isosceles. In theory, if you connect PM or PD or DB, all of those would create isosceles triangles. The reason that is because our triangle is composed of 2 radii, okay, 2 radiuses, and because the radius of a circle, any radius of a circle is going to have the same measure. Any triangle that you create this way using 2 radiuses and a chord is going to be an isosceles triangle. So the same type of triangle, the answer to that question would be yes. So that's 6A. Now we're looking at 6B. Are all circles similar? Are all circles congruent? So if you remember similar, okay, if I have a square here and then I have a bigger square, okay, these 2 squares are similar because they follow the same set of rules in creation. Like in order to create a square, they need to be all equal side lengths, all 90-degree angles, 2 sides that are parallel, right, all that good stuff. Now, of course, this is not perfect, so we can imagine, okay. So square, square, they are similar, okay, but they are not congruent because congruent squares are squares that the same size. So if we can imagine that these two are the same size, these two squares would be congruent and similar. Okay, so if something is congruent, it is also similar. If something is similar, so like these two, it does not necessarily mean that it is congruent. Congruent shapes are shapes that have this, that are the same in every way. So are all circles similar? So imagine how we create a circle. If I draw around a point, okay, and then I draw another circle, a bigger circle, okay, even bigger circle, right? I'm creating those all about the same way. They all go around a certain point, okay, a center point. So they're all created in the same way. So yes, they're all similar, but are they all congruent? Well, we can look just by what I've drawn here, okay, that all of these circles are not the same side and or not the same size, and because they don't have the same perimeter or circumference, if you remember that when talking about circles, because they don't have the same perimeter, they don't have the same area, because they don't have the same radius measure, all of those things, because they aren't exactly the same, just looking from this one to this one, because they aren't exactly the same, they aren't congruent, but they are both circles. So our answer to that would be no, they are not all congruent. So number 7 here, this was a bit of a confusing one. It says, what conjecture can you make about this type of triangle? Okay, so this type of triangle, the one that you created, was an isosceles triangle, and I did this in class too. So what conjecture can we make about isosceles triangles? And I'm just going to put a little S there. Okay, cool. So what conjecture can we make about isosceles triangles now that we have done this exercise? So if you look at my diagram right here, okay, we already know that isosceles triangles have side lengths that are the same, which we measured, and we confirmed that these two side lengths are the same. So now, if I already know the side lengths about that, the only other information that I have about this triangle that I've created is its angle measures. Because we used the protractor, right? We got 45 for this one, and then we used process of elimination, knowing these two angles to find out what this third angle was. So, what conjecture can I make? Well, I'm going to say that it has to do with angles. And then, so if we look at our diagram, or our picture that we drew here, what do I notice about the angles? Well, some people would maybe say that all isosceles triangles have a 90-degree angle. That, in fact, is not correct, because I could create an isosceles triangle that is tall and skinny like this, where these two sides are the same length, right? But this angle right here is not 90 degrees. It's much too small, and then these angles are also not 90 degrees, okay? So it is possible to have an isosceles triangle without 90 degrees. So if I was looking at something else, I would say, you could maybe say that, well, so if an isosceles triangle doesn't have to have a 90-degree angle, that also means that they don't need to have 45-degree angles. But if we were to step back, and instead of looking at the specific angle measures, if we step back and look at how they are related, we can say, okay, pretty safely, and this is actually what they're trying to get at, is that two angle measures of every isosceles triangle are going to match. Okay, so what conjecture can you make about isosceles triangles? That they always have two matching angle measures. Okay, so, and then you can see even in my example isosceles that I drew here, here's one angle measure, and here are two angle measures. These two little angle I guess little angle denoters, these little things that tell you that it's an angle, because there's two of them here and two of them here, that means that they are the same angle measure. And I did that on purpose because isosceles triangles will always have two angles that match. And you can kind of see, even if you're drawing imperfect isosceles triangles, you can kind of see how that would be true, right? We can see that these two angles look like they're the same. Okay, and then we have our one that we drew perfectly, we constructed it, and these two are the same. So you can imagine kind of just spitballing a little bit, drawing these just as they are, maybe with an acute angle at the top, maybe with an obtuse angle at the top. Okay, you can see that these angle measures would also match, which leads us to believe that all isosceles triangles will have two matching angle measures. There you go, ladies and gents. That is section 1.1, or excuse me, activity 1.1 of topic 2, packet 1, or lesson 1. I hope you all have a wonderful day. I will talk to you soon. Adios.